Hello, my name is Dilip. In this session, let's talk about classic parallel database systems. Coming to the background, basically the data revolution started in 1990s. This was the time when a lot of data started coming in from various domains like forecasting, molecular modeling, oil and gas. And these data started coming in various formats like text, videos, images, and different formats. Basically, because of increasing volumes of data, and that too data of varied forms, the need for a decision support application arose. So basically, the data was coming in, and there was a need to analyze the data, right? This was when the concepts of data mining got evolved. So basically, when the data was coming in, a large complex queries were performed on large volumes of data. And that is where the need for the more powerful system actually arose. So workloads on the single database systems were not able to handle like these large volumes of data, and complex queries on these different kinds of data were basically not possible on a single instance database system. So that is where it fueled the need for the parallel database systems. Coming to the introduction, the first kind of parallel database systems were called as classic parallel database systems. So these were the systems which were made available with parallel data processing, and it was basically on RDBMS. And when we say RDBMS, it followed SQL, that is declarative SQL, which is a query language, the normal SQL that we use. So basically how these parallel database systems were developed, and they followed all the steps which were used to build a normal database system like query processing, execution engine, and partitioning of data, which was very much needed. So all these steps of plan, execution, and explain plans, and various steps of that were used or that were developed while creating a database were again made or were again done or redone for a parallel database system. So basically, one such important aspect of a parallel database system is the need for high performance and scalability by partitioning the table across multiple nodes. So when we say classic parallel database systems, we had different servers, say server 1, server 2, and server 3. And nothing is shared between these servers. Every server had its own memory and CPU, and basically even storage. So the database was actually partitioned across each server. So one server had a part of the database, the other server had another part, and the third server had other part of the database, right? The data was actually partitioned and split across multiple nodes so that a parallel execution of the data can, or the parallel processing of the data can happen. So that is where idea of classic parallel database system occurred. So basically it is a high performance and scalable database, multiple databases connected together, and the data is partitioned across multiple tables. So such a partitioning scheme enabled relational operators like filters, joins, and aggregation. Like I said, everything starting from query execution, joining, and using of relational operators, everything was done on these parallel database systems like it is done on a single node database. So coming to the architectural choices, while building a classic parallel database system, what were the architectural choices that were available? So first one is shared memory. So in shared memory, all processors or all servers share a common central memory and all disks, right? But the issue with shared memory is the memory is limited. You cannot scale this again, right? So memory becomes a bottleneck. And share disks. Each processor has private memory, but all processors shares the same disk. Again, this becomes expensive at scaling when it comes to disks, right? So connecting all the processor to disks involves multiple things to be done, right? The memory is different for all the servers, whereas the disk is shared. So again, the IO becomes a bottleneck in case of a shared disk. And the third one is share nothing. Nothing is shared between the servers. Each server had a processor, memory, and a disk, but the network is shared. That, like I said, all the servers are connected through a shared network. So classic parallel database systems basically applied the shared nothing architecture. So these are some of the examples of classic parallel database systems like Aster and Cluster, IBM DB2, Grafana, Greenplum. IBM DB2 is one of the oldest databases along with Oracle and Microsoft. So in the 1990s and 2000s and 2010, there were three important databases that were mainly dominating the market. One was Oracle, other one was Microsoft, and then came IBM DB2. So Oracle Ncube, also known as Oracle Parallel Database Systems, which is now called as Oracle RAC. And SQL Server is from Microsoft. So basically the motivation, what is the motivation in building a classic parallel database system? Like I said, large volumes of data sets in various domains and in various formats, and the need for analyzing these large data sets. It is important that the data is coming in and we have to analyze this data in a speedy manner. So that is the motivation. And the problem statement is basically to develop a massively parallel database system to cater the needs of decision support applications and handle complex queries on large volumes of data. Like I said, the need to analyze the large volumes of data in a faster manner requires a parallel database system. And that is the problem statement, is to create a massively parallel database system. And the challenges that were faced is one of the challenges that is not mentioned here is when you build a new database system, you have to adhere to all the standards of a normal database system. Like I said, the query processing and storage, IO, memory configuration, the execution plan, and everything from start to end, all the standards that were followed in building a proper database, RDBMS based database, where all need to be followed when you are building a database system, that is a classic parallel database system also. And the cost of ownership and scalability, right? When you are building a huge database, parallel databases with many servers connected together, obviously the cost is high, and the scalability also, like how much can you scale it, right? As the data keeps coming in, terabytes and petabytes of data. Diversity of the data is also a point, right? Like I mentioned, there's different kinds of data that are coming in, and the need for shorter intervals between data coming in and analysis of that data. So issues addressed, like I said, the need for building a classic parallel database system required everything to be followed. So a highly scalable architecture for parallel processing and analyzing massive data sets. Proper partitioning of data was required. Since we are not since we are using a shared nothing architecture, the schema had to be predefined, right? How are you going to split your data across multiple partitions in multiple servers? That needs to be predefined. So that was one of the main concern of building a parallel database system, is you are partitioning the data beforehand. All the data cannot coexist together. You need to partition the data. And nodes, one node can have only one type of data and the other node can have only one type of data. Like that, we had to design. And the execution engine designed for various execution operators supporting multiple use cases. We will see one by one in the coming slides how an execution engine was developed, how a query optimization approach was developed to finalize on the best fitting execution plan, and the splitting of a plan into multiple executable tasks and scheduling them across the nodes, right? Managing the resources at the node level. What are the resources that we manage, be it memory, storage, how are you going to manage, and how to mitigate from task failures and query failures, and finally, how do we maintain the systems? All these issues were addressed. We will see one by one how they were addressed. So data model and storage layers, basically, like I said, classic parallel database system supported a relational data model, that is SQL. And two features. One is simplicity. A well-defined schema helps with cost-based query optimization to keep data error-free. This is one of the main tasks of a classic parallel database system, is that you predefine the schema. How are you going to partition the tables and the data? Rigidity, longer initial application development due to defining the schema upfront. Like I said, once you define the schema, it is very difficult to change it during the development phase or once you have implemented the system. So it is very important to have the schema, that is the data predefined, like which partition has what kind of data. And to the storage layers where you are storing the data, there are multiple partitions that can be done on a table level, starting with range partition. It is done based on a date column. So if we have a table which is having a date column, then you can do a monthly partition on a date wise, like so and so months, all transactional data of say April is stored in one partition, of May is stored in a different partition, of June it is stored in a different partition. That is range based partitioning, partition based on date range usually. Coming to list, you can also partition a table on list partition, say region wise. Asia's data is stored in so and so partition, or Europe's data is stored in so and so partition. That is list based partition based on a list of values. Now coming to hash partitioning. Hash partition is on a hash function where you do not have a specific column to partition the data. That is where you do hash partitioning. Random partitioning is unlike hash uses a hash function, whereas random partitioning, it uses a round robin fashion. The data is round robinly assigned in various partition in the form of tuples. So hash is better when compared to random. Block partitioning is done for a kind of partitioning where you are storing the consecutive blocks. So when you get the data in form of batches, so you store the consecutive blocks in a partition. So when you are retrieving any sequential data, all the consecutive blocks are available in the same partition. So that is where a block partitioning is useful. So this is one of the examples on how a partitioning is created on a parallel database system. So basically you start by creating a node group, say node group A, and you are assigning nodes 1 to 10, or you can also assign say nodes 2, 4, 6, 8, and 10 to node group B. And when you are creating a table, you can say, okay, this table belongs to group A, which group, group A or group B, and how are you partitioning, using which column, and what is the technique you are using, right? You are using a hashing technique. You are partitioning based on a column A, and you are storing the data in a group A. So group A consists of all nodes, say 1 to 10. So this was the way in which the partitioning was done in a classic parallel database system. So degree of declustering, concepts of node groups. This was the concepts of node groups. Co-allocation. Co-allocation is you are allocating a similar kind of data together in a single partition. So that is co-allocation. The important point here is when you use co-allocation, you get a lot of performance gains because there is no need to join multiple partitions from various nodes. If the data is all existing together in a single partition, the joint condition becomes less expensive, right? That is the advantage of co-location. And you will also gain time instead of transferring the data from one node to another node. Then that data transfer time is also gained when you are using the co-location. That is storing the relevant data which is used for a joint condition co-located together in a single partition. Replication, fault tolerant, right? You can also use two different nodes. One node group uses a set of data stored, and the other node groups can store the mirrored data. So that is fault tolerant replication. So now coming to how execution engine was developed. So execution engine, it started with the development of a coordinator task. So this coordinator task is responsible for basically splitting the plan into multiple suboptimal execution plans, right? So this coordinator task will split the plan into multiple execution plan and assign it to different nodes. Then coming to basically what are the different types of operators. So co-located join is operator, which is basically locating the data together in a single partition. So when the data is located in a single partition, we use co-located join. In that case, like I said, there is no need of getting the data from another node group. The join condition becomes easier and less expensive. Directed join operator is basically when you have to get the data from a different partition, right? So you basically transfer the data from one partition to another partition and then do a join. So data existing in two different partitions. Repartition joined operator is basically if one partition is there and the other partition is also there and both are not at equal volumes of data, then probably there may be a need to repartition. So online repartitioning is also possible. So repartition join operator is used when you have to repartition the data in runtime. So that is repartition joined operator. So probably you will get data from another server and then repartition it accordingly and then do a join operator. Broadcast join is you get a complete table. So let us say you're joining a big table and a small table. So a small table is fragment and replicate join. You get that small table from the different server and put a copy in all the servers wherever the join has to take place. That is broadcast join operator. So the difference between broadcast join and directed join is broadcast join is getting a small table from a partition and fragmenting it across or broadcasting it across all the servers. Whereas directed join is you are getting a portion of a table from a partition to a different partition and then doing the join operation, right? Like I said, partition parallelism, pipeline parallelism, and independent parallelism. These were the different kinds of parallelism that were applied. So when you are doing a different kinds of join operators across the data, you can actually fetch the data from a different partition. Of course, it becomes expensive when you get the data from a different server to another server. The data transfer latency is always there, right? But that is a point, right? If you have the data properly split across all the partition, and there is no need to get the data from a different partition, then your parallel database system is working fine. But there are always cases when we will have to get the data from a different partition, and that is where this different join operators comes into picture. So basically, how will the system know in which partition is the data available? So there are different papers again that were submitted for split tables. So there is this Gamma paper for a Gamma database. They were using a table known as split table, which used to maintain all the different information, metadata about which partition is having what data, right? Then came table queues. Table queues is furthermore advanced. It is kind of a map table which was used by IBM DB2, which is also used to maintain the list of partitions and tables. And then came exchange operators, which was much more advanced. And this was from Volcano database. So this exchange operator also had a coordinator task pipeline to it. So this is about the execution engine. Now coming to query optimization. So basically, once the execution engine gets to know where are the data available and which operator join should be used, like we discussed, it is going to split the plan into multiple execution plans. And then it is going to basically use a scheduling algorithm to assign the subplans to different nodes and then allocate the resources. So basically plan selection, it chooses the best plan from the previous step, and then it uses the scheduling algorithm to basically split the plan and transfer the plan to the respective nodes wherever the data is available, and then also determine how much CPU, memory, and IO to be allocated. So plan selection commonly refers to query optimization, involves ordering and choosing join operator, access path selection for the tables, and choosing the appropriate cost metrics for resource optimization. So query optimization approach, there were many optimization approaches that were used apart from the join operations. Like we discussed, the two-phase approach was an early approach. Start with a serial plan, post optimization applied to transform serial plan to parallel execution plan. So you start with a serial plan, and once you know where the data is available, then you can use a parallel execution plan in executing the plan parallelly across various nodes. Apparently, this approach missed good plans in shared nothing system, since serial plan assumes plan will run on a single node. So this was a difficult approach because you tend to miss the good plans if you start with a serial plan and then try to transform to a parallel plan, right? We have various systems, and most of the systems go underused, right? Then semi-joins came into picture. Semi-joins is basically, instead of doing a full join on a complete table or a complete partition, you just get the data based on the where clause. You get the data that is required and then do a semi-join. Instead of getting the complete data, read the where clause, do a semi-join, right? So the use of partition pruning, right? Exclude the partition tuples and only get the data that satisfies the filter conditions to do a semi-join. So partition aware join, like we discussed, the different database had different kinds of tables like split tables and all, which used to maintain the data about where the partition is there, what kind of data is there. So that is partition aware join. That was also useful in speeding up the query. So estimating the cost of the plan is again dependent on latency, complete to plan execution, which is not properly estimated in parallel plan, which is overcoming using many plan selection algorithms. So basically many plan selection algorithms and scheduling algorithms came into picture, and the best one was used, which used less resources and which made use of the data that is available across all the partitions. So adaptive plan selection is proposed to minimize errors while estimating plan due to unknown data properties and uncertain resource availabilities. So adaptive plan execution is a paper that was published in 2004, but Oracle actually applied this feature in 2012 with Oracle 12c. That is where adaptive plan selection, that means in runtime, it is going to change the plan which it thinks is the best. So maybe it starts with a bad plan, but during the runtime, it will always look for the better execution plan and it adapts to it, right? So this is a perfect example of how today's research can be tomorrow's feature that got implemented into a real-time system. So that one example is adaptive plan selection. Scheduling, like I said, different. So once the plan is developed, plan is broken into sets of executable tasks, and these tasks are scheduled to run on the nodes of the parallel database system. So approach one was based on functions shipping, whose goal is to run the computation as close to where the data is stored, right? So like most of the time, it is not possible. Most of the time, the data may not be co-located, right? The data can be vastly spread, and there is a limitation here that is the limit of the size of the search space, right? The second approach is first determine the execution plan and then use a scheduling algorithm. So first determine the execution plan, know where the data is there, then define a scheduling algorithm by breaking the plan into multiple suboptimal plans, and then move these plans accordingly to where the data is there to that node, right? So basically a shelf algorithm was proposed for static scheduling. So there will be multiple shelves that are available, and a task is allocated to a shelf. The shelf knows, okay, this task is going on and this particular node is taking care of this task. So eventually the subplans keeps getting added to the shelf, whichever is free. So that is shelf scheduling algorithm. So shelf scheduling algorithm, it is basically, like I said, for each of the remaining tasks that are not assigned to a shelf, the task is either assigned to an existing shelf or a new shelf without violating the precedence constraint. So this is one of the main thing that it took care of. That is, it should not violate the consistency constraints. That is, the data should not go inconsistent since you are splitting the plan across multiple plans, right? And static scheduling algorithms cannot react to issues arise during task execution, right? Once you split the plans and if there is any issue that occurs, then the static scheduling algorithms cannot react to it, right? So because of which a dynamic scheduling algorithms was also proposed, which will react to the problem by migrating task execution from one node to another node at the runtime. Resource management. So how were the resources managed? The resources were managed either at the individual node or at the entire system level. Ability to tune the performance of individual nodes based on the hardware capacities, database partition size, and workload. So scalability, you can always add new servers and split the partitions furthermore, right? When you are able to scale, you start with 2 servers, 3 servers, 4 servers, and then you keep on adding. It is horizontal scaling, unlike vertical scaling where you are adding more and more CPU, compute, and storage resources to a single server. So partition parallel processing is the key enabler for linear scalability. So like I said, your data should be flexible enough and the schema should be predefined so that you partition the databases beforehand only. One challenge here is the data may have to be repartitioned. Yes, as you keep adding the servers for scalability, you may have to repartition the data as you add or remove the servers. Most commercial parallel database supports online reorganization, known as online reorg, which is again one of the new features of Oracle 12c, which was released in 2012. Online reorg was one of the new features which was done on 2012, whereas this papers on parallel partition databases were long before proposed. Fault tolerance, right? Task failures. You basically want to mitigate this fault tolerance, mitigate the task failures that happens due to node crash, misconfiguration, or memory executed, or even data failures that happens because of disk failure. So task failure remedy is you have to convert a task failure to a query failure using two-phase commit that we already know how a two-phase commit works. And if you are able to convert a task failure to a query failure, then that query can always be re-executed by maintaining the constant consistencies, right? Fine and tolerant techniques like OSPay, which divides queries into subqueries and replicates data to multiple nodes, right? The fault tolerant, you cannot have a data only in one partition, because if that particular node goes down, the entire data goes down. So like I said, you can replicate your data to multiple partitions by using mirroring technique, right? So in that case, any disk crash happens or any node crash happens, your task can be rerun from the another node where the data is mirrored. So data failure remedy. Several techniques have been proposed for data availability in case of node failures, like I said, again, data replication, mirror disk, data clustering, disk arrays with redundant check information, and chain declustering. System administration. So these are the basic tasks of a DBA, which he does, that is while doing the system administration of a parallel database system. Like he has to apply the hints on the queries. Applying hints will make the queries run faster. You tell them, okay, this you use this index or you use so and so index to do a search on so and so query, or you gather the statistics. Gathering the statistics of the table means the metadata of the table is aware of how many rows are there, what is the level of fragmentation, and what is the size of the table. If you don't gather the statistics, basically the bad plans are chosen. That means the query optimizer is not aware of the actual size of the table if the statistics are not gathered. If you gather the statistics and the statistics are up to date, the query optimizer is aware of the size of the table, and then it will design a plan accordingly, right? You have to choose the right set of indexes, rebuilding the tables and indexes as part of maintenance activity to avoid fragmentation. So all these are the tasks of a system administrator. Hardware with the right amount of processing memory, disk, and network bandwidth, controlling data layout with appropriate declustering, partitioning, and replication, like database schema architecture with proper denormalization in order to make query execution more efficient, setting the threshold that controls the policy of admission control and load balancing. Like again, these are all basic system administration tasks that involves the uh, involvement of the system administrator, the operating system, the Linux administrator. You have to do a proper sizing. You have to predefine the schema. And whenever the time comes, you have to rebuild the tables, indexes, and do repartitioning to avoid fragmentation. And you have to also choose the right parameters for the memory, buffer pool, heap size, and all the kernel parameters have to be set properly. All the database parameters have to be set properly to ensure that the system works seamlessly. So this is always an ongoing activity. Future works as on that day. Uh, Basically, when this paper was published, all the prerequisites were met in designing a proper database system, parallel database system, using a shared nothing architecture. So classic parallel database system, though it was developed properly, it had many hurdles in terms of scalability, cost of ownership. Like I said, the data coming in were large, the data coming in were diverse in nature, and the demand to analyze those data in a speedy manner was also increasing. So this only a parallel database system could not suffice. So there were much more innovations required. So innovations in terms of addressing the deficiencies of a classic parallel database system, like I said, right, which related to performance, and you are using a query language, and query language may not always work for different kinds of data like images, videos, and all, right? So innovations were furthermore required, and then came the different kinds of systems that evolved, that is columnar systems, MapReduce systems, and data flow systems. So real-time examples on partitioning. At the end, I am going to show you some partitioning scripts wherein how we partition a table in real time in Oracle. So we partition a table of on a 140 terabyte database. How do we partition on an enterprise application? We will see that, and we will see parent table, parent child reference partitioning example, how it is done, and the advantages. And so basically this is one of the implementation. The use cases differ case by case, right? Not always you can use this kind of partitioning technique. It depends on what kind of data you have and how do you use that data to partition the tables. So the approach that we show, it was useful because it is easier to archive the data, because we are working on a large OLTP database of 140 terabytes in size, and the data that was coming in is transactional data, right? So once the data keeps coming in terms of gigabytes and terabytes, you will have to sometime take a decision to archive. So the way you partition is important to know how do we archive the data. So this is an example of Oracle Real Application Cluster. It is a parallel database system that is currently in use by Oracle, known as Oracle RAC. It is a shared everything architecture. Surprisingly, a classic parallel database system was a shared nothing, but this is shared everything. Mainly the storage is shared here. The storage is shared, and the storage was in the form of raw disks, and Oracle developed a technology known as ASM, Automatic Storage Management, which manages these raw disks. And there were two nodes, basically two servers accessing the same database. And application used to connect using a SCAN name known as single client access name. It was a single IP which was mapping to both the nodes. How it was mapped? It was mapped using BIP. So the networking aspect also comes into picture here. So SCAN had basically three IPs, which was running using the SCAN listeners. And when client accesses, he accesses only using a single IP. So this way you can add or delete the nodes without actually client knowing. Client only knows the SCAN name. But internally, each node has its own IP and it used to register with the SCAN name, right? And like I said, the storage was shared across the two nodes, and it was shared using the ASM, Automatic Storage Management. And one important question that can be asked here is, how were the two servers communicating? Because this server had its own memory, this server had its own memory, right? Only the storage was shared here, right? And it's actually shared everything. Not it's basically a shared storage architecture, not shared everything. So the private interconnect known as Cache Fusion was another technology that was developed by Oracle to manage these kind of system, right? There is a memory for this server, there is memory for this server. They used to communicate using the private interconnect, and there was a system of cache fusion, right? If an update happens through this, and the update also is happening through this, then the both go and communicate using the cache fusion, and only then the latest value is updated on the database. So this is an example of Oracle Real Application Clusters, which is currently in use by Oracle, which is an alternative to a parallel database system. So basically, parallel database system evolved and it became Real Application Clusters. So like I said, Oracle did two important things. One is ASM for shared disks, and one is cache fusion for private interconnect, memory interconnect. Oracle Exadata machines are physical machines. So Oracle sells them as physical machines to the customers. They internally use this rack database architecture, like I said, ASM, but they also have many things that were done to improve the storage layer. They had some Exadata cell servers. The storage servers were very powerful. These are the latest trends. These are the latest machines, very powerful machines of Oracle, known as Oracle Exadata machines, which uses many technologies at storage level, like cell servers and IORMMS, RSOEL, right? All these are within the storage servers, right? They improved the storage servers. They developed the physical machines. It comes in quarter rack, half rack, and full rack machines. And they are of different configurations, and internally they follow the rack database architecture, and these are costed in millions of dollars. So conclusion and observation, like we have seen till now, how a classic parallel database system was developed by following all the standards of a normal single instance database system, and how it was basically done, like all the query processing, scheduling, query optimization, different types of joins and scheduling algorithms, everything we have seen. What are the advantages? What are the disadvantages? One of the main disadvantage was predefining the schema, right? Partitioning the data across multiple nodes. We have seen everything, and we have also seen what is the future work that were done in terms of MapReduce. Like different things came up, like columnar database MapReduce was done, and different things to improve upon the classic parallel database system. And before we wind up, let me show you the partitioning scripts that I said I'll be showing. And basically, this is how a partitioning script is prepared. So we create a table space for every month. So this table space has a data file associated with it, and you assign this table space to the table. So when you create a table with a set of the columns here, how are you partitioning it is basically I am partitioning it by range on a date column. So ILM date is a date column here, and then measurement component ID is a ID column, right? Measurement component ID is an ID column. So I am subpartitioning it. So subpartitioning template is this one. I am creating 20 subpartitions for a single partition. So measurement component ID is a 12 character. So I basically split the numbers into 20 partitions into 20 partitions with 12. So these are 12 digits, since it is 12 char. And then each partition, say January partition, is allocated the January month's table space, and with the date range column. So the date range column is based on the ILM date. So like I said, this is how we partitioned it in real time with a pmin, and there is also a pmax partition. It was partitioned for 6 years. And as you see, there are columns like CLOB columns here. So these CLOB columns need to be stored as secure file because these are huge data, character large objects, and which requires compression also. So row compression, medium cache, and store as secure file, right? And every partition is also using that lob clause, right? So for example, Jan month's partition is date less than Jan 2021 is date less than 1st February 2021. All the data goes into Jan. So the advantage is after 4 years, if I want to archive this partition, I can archive it easily. I can take a backup of this partition, store the backup somewhere, and basically truncate the partition, right? So even indexes were partitioned accordingly. So this is the primary key column, and the index were partitioned with a separate data file for the index, right? I have indexed 20 partitions here by splitting the primary key, and then added that as a primary key. Then there were secondary indexes also. So this is how we partition. And now, how were the child table partition? So this is the child table of the parent table I just showed. It was partitioned using reference. So we created a foreign key on the init measurement data ID of the child table, and it is referencing to the parent table. So it is a reference partition, right? So any data that is there in the child table will also have to be there in the parent table. So this is tightly coupled database system. So SQL is a very tightly coupled database system that follows the ACID properties. So yeah, this is an example of how the partitioning is done in real time. That is it that is it all about the classic parallel database system. Thank you.